So in the following example, we're giving a pathogenesis curve for a measles infection. And we're going to see how this formula to calculate the area between two continuous curves is going to help us to compute the level of infectiousness for some particular patients. So this is the pathogenesis curve for a measles infection. It shows how the disease develops in an individual with no immunity after the measles virus spreads to the bloodstream from the respiratory tract. So this is the first day, 0th day, and then this is the 21st day. So the symptoms going to appear on the 12th day, and over here is on the 21st day, then it's clear. Okay. The patient becomes infectious to others once the concentration of infected cell becomes great enough, and he or she remains infectious until the immune system manages to prevent further transmission. However, symptoms don't develop until the amount of infection, which is a particular threshold. The amount of infection needed to develop symptoms depends on both the concentration of infected cells and time, and correspond to the area under the pathogenesis curve until symptoms appear. A. The pathogenesis curve in this figure has been modeled by this function. If the infection begins on day 10 and ends on day 18, what are the corresponding concentration level of infected cell? Now, to find this corresponding concentration level of infected cell, then we can just substitute this number into the T over here, because F of T gives you the concentration level of infected cell. So substitute 10 into the T here, we're going to get 1,210. The unit here will be cells per millimeter. If we substitute 18 on the 18th day, we're going to substitute 18 into the T into this function. We're going to get 1,026 cells per milliliter per ml. Okay. B, the level of infectiousness for an infected person is the area between this curve and the line that go through the 2 point P1 and P2. With P1 having this T coordinate to be T1 and P2 having this T coordinate to be T2. Okay. So this area that is between this curve and this curve is the level of infectiousness for a particular patient. Okay. This patient, T1 is 10, T2 is 18. The level of infectiousness for this particular patient will be this area between this pathogenesis curve and this line segment over here. Okay. So we want to compute this area. Now we can use the formula that we have to calculate this area between these two curves. But first we need to have for this curve, this pathogenesis curve, we already have this function. However, we don't have a function for this line over here yet. However, we can find out. Well, if we given 2 points on this line right here, we can calculate the slope using the slope formula. Once we get the slope, we can use the point slope form to write the equation of this straight line. So n minus this n1 here will be 1210, will be equal to the slope, negative 23 times parenthesis t minus t1, which is 10. Now, if we isolate this n will be equal to negative 23t plus 1,440. So that's the function representing this straight line right here. So the area between this function f right here and this line over here is given to be this integral. The integral with respect to t, where t go from 10 to 18. So start from day 10 to day 18. So integrate from 10 to 18. And the function above right here, and that's ft. And this function over here, we found that to be negative 23t plus 1440. So the function on top, subtract this function down here. So substitute ft equal to what they were given. That was this function right here. If you multiply this out, you're going to get negative t cubed plus 20t squared plus 21t. Now subtracting this, that becomes this part right here. And you combine like 21t plus 23t is 44t. Now we find anti-duality. So once we find anti-duality, and we just need to evaluate this from 10 to 18, and the result here turned out to be 1,877. So the level of infectiousness for this patient is about 1,877 cells per millimeter days. All right, so let's take a break. Okay, let's take a break.